Okay, so we're leaving the linear momentum stage, going into the angular momentum stage. And with angular motion, a lot of the same rules apply, but yet they're different. So, first off, when you talk about how you describe motion, if it's just linear motion and this thing is moving along, hey, simple. It's moving at 5 meters per second, whatever that number is. But if you have angular motion, you have to be able to deal with two situations. Situation number one, you can have the wheel spinning, but it's stationary. Situation number two, you can have the wheel spinning and it's moving at the same time. So you have to be able to deal with stationary motion and linear and angular motion at the same time. So that gets a little bit complicated. The other thing that happens is that when things spin, they do weird things. So if I hold this wheel up like this, okay, so I'm just holding it on this side, and I let go of it, it does exactly what you would expect. Oh, it falls, gravity is acting on it. But if I take that wheel and I spin it and then hold it up, then it stays up and it rotates around. And if I spin it in the opposite direction, oddly enough, then it goes around, it still stays up, but then it processes in the opposite direction. And this is what we're going to get into tomorrow with angular motion. So, the other thing that you have to change is the variables. So basically, all the good variables were taken by the linear people. Distance, velocity, that type of thing, acceleration for A. So the angular motion people said, fine. Maybe they were all in a fraternity, I don't know. But they decided to use the Greek alphabet.
Cringe.
No, certainly not the French.
No, cringe.
Oh, I thought you said French.
No, I hate the French.
The French alphabet.
Yeah. French suck.
That's facts.
Okay. So if you don't know your Greek alphabet, you have theta, omega, and alpha.
Theta W fish.
Well, here's what, and everybody thinks you're clever, and then they think there's the first one to say this, is that they go, that looks like a butt, okay? And you think you're the first person in the history of the world to make that observation. You go, that looks like a butt. You're not, okay? We all know it looks like a butt. Get over it. So a lot of times we'll refer to it as theta butt fish, okay?
Okay.
So those are your three variables, theta butt fish. So here's the story. So just like if I have to keep track of how far that moves, I have to keep track of a point on this wheel and how far it moves around. So theta is equivalent to distance. The distance is measured in meters, which makes sense. Cool. Travels 5 meters. Got it. Not a big deal. But when you're dealing with things that spin, we have to use a new unit. So in angular motion, we use radians. Okay? Now, if you don't remember back to your days of studying in the circle, one revolution goes through 360 degrees, and how many radians are there in one revolution? 2 pi. 2 pi. Now, here's the other thing about radians, is that it's one of the very, very, very few instances where you have what's called a dimensionless number, okay? So you're not going to say 2 pi radian meters or 2 pi radians meters per second, okay? It's just 2 pi radians. There's nothing associated with it. It's just, that's it, 2 pi radians. So theta is equivalent to distance. Are we going to have, like when I spin this thing, well, how many revolutions did it make? Did it make 2, 3, 4, 5? How far did it spin? How many revolutions did it make? So omega is the equivalent of velocity. So in linear velocity, that's in meters per second. Oh, how many meters per second did the squirrel run across the street. Boom, there you go. But instead of meters per second, omega is going to be in
Radians per second.
radians per second. Is it spinning really slowly where you kind of go slowly like this, okay? Or does it move faster? So it's the same idea. The bigger the number is, the more radians per second that it travels through. Now, here's the conceptually difficult part about this. Is that if I tell you, hey, I'm going to go out the hallway and I'm going to run 6 meters per second. You all can visualize that. Oh yeah, right, 6 meters per second. Okay, that's a decent run. Okay, you guys can visualize that. But if I say something's moving at, 41 radians per second, it's like, is that fast? Is that slow? It seems like it should be fast because it's 41. I don't know.
Radians like.
Okay? Yeah, it's like, see, that's the tough part about angular motion, is that you talk about it, but this is one of the few instances it's tough to look back and go, does that really seem like a viable number? Now, so alpha, oddly enough, is equivalent to acceleration, which is in meters per second squared, but alpha then is going to be, oddly enough, in radians per second squared. Okay? Now, Newton's laws still apply, oddly enough. So if I don't apply a force to this wheel, it's not going to speed up. Okay? Objects don't want to spin unless you apply a force to them. But once you get them spinning, what do they want to do?
Keep spinning.
They want to keep spinning, because they're going to keep spinning until you apply an outside force to it. And the same idea. If I just apply a little bit of force, I just get a little bit of angular acceleration. If I apply more force, I get more acceleration. Okay? So in many ways it's the same, but yet it's not. Now, there's some crossover equations that allow us to cross this bridge. And this is on those sheets that you've got. So you've got D equals R theta, V equals R but, A equals R alpha. So what do all of these have in common?
R.
R. Okay, yes.
In our in the pre-calculus class, we say velocity equals wide receiver because it looks like a W. Like if you reverse the order, it looks like WR.
Okay. I can see that. I like R but better.
Okay.
I like my butt.
No, let's not talk about that.
Our.
No, let's not talk about that either. That's even weirder. Okay,
Our.
so here's the story.
Communism.
So we're going to back up and we're going to act like none of this exists. So the diameter of this wheel is 0.5, which makes the radius then 0.25. Bless you.
Thank you.
So here's our wheel. It has a radius of 0.25 meters. So here's what I want to know. If I start with this piece of tape right here on the bottom, and I roll this thing along like this, how can I figure out how far that's going to go before that piece of tape gets back to the bottom?
The circumference of the
The circumference of
outer
the wheel.
diameter.
Okay. So how do you calculate the circumference of a wheel?
2 pi r.
2 pi r, which would be 2 times 0.25 meters. Now, I know all the math people will tell you, oh, leave it in terms of pi because that's more precise. And mathematically they're right, okay? But here's the problem. Meter sticks are not measured in units of pi, okay? Yes, this is 1/4, which makes that pi over 2, right? Well, meters. Well, I'm not going to find a meter stick that says, oh, let me find pi over 2 meters on the meter stick, okay? It's not there. So mathematically, that's the pure answer. Realistically, it doesn't work. So when you're actually doing this, get it into the decimal form, because that's what you're going to measure in. You are going to measure the pure decimal form of these values. Now, you go, okay, well, that's cool, Burkamp. Can we use these new crossover equations that you just explained? It's like, well, I don't know, let's give it a shot. So if you look at this and you have D equals R, which is 0.25 meters. Now, if it makes one revolution, which it did, how many revolutions did it move through? One. One revolution is how many radians?
2 pi.
2 pi. Oh, so you get 0.25 times 2 pi. And oddly enough, you get the exact same answer, which is just going to be the circumference of the wheel. Now, obviously, if it makes 2 revolutions, it's going to go twice as far.
4 pi.
Now, here's the other odd thing about this. Once you're dealing with angular motion, sometimes radius is a factor and sometimes radius is not a factor. And that's going to be an important thing to keep track of. So if I take this 1 kilogram mass, okay, and I put it on the table, and I'll put a mark on here, okay, there. And so I'm going to roll this thing around until that mark comes back up to the top. So if did this go through 2 pi radians? Yes. That made 1 revolution. But did it travel the same distance as the wheel did when it made a revolution?
No.
So if you look at making a revolution, 5 revolutions, whatever it is, the radius is not a factor in the equation, okay? But if you look at the transition from distance, linear distance, to involving theta, then radius is going to become a factor. Now, here's the other odd thing. So you have D equals R theta. Cool. And we just said, and somebody actually get me the number, take 0.25 times 2 pi.
1.57.
What'd you get?
1.57.
1.57 meters. Cool. Now, let's say that the radius was twice as big. So let's say we have a radius of 0.5 meters. Okay? So if the radius is 0.5 meters times 2 pi, you're going to get
3.1.
3.14 meters. Now here's the $1 million question, amongst many in this world. Is that a linear function?
Yeah.
Well, you shake your head, yes.
Yes.
Good. I'm skeptical. That doesn't look like a linear function to me.
Well, you're wrong. How do we- 2 pi is a constant.
Oh, hold on. Stop the bus. Could I graph that on the y-axis?
Yeah.
Okay? Y equals mx, right?
Yeah.
So I could graph that on the y-axis, and I've got 2 points. I've got 1.57, and I've got 3.14. True? Could I graph theta on the x-axis?
Yes.
So in this case, theta would be, how many radians did it move through? 2 pi, right? So here's the story. So I've got theta here, 2 pi, right? So I got 2 pi, and then I've got 1.57. So, oh, I screwed this up. So let's say I made 2 revolutions. If I made 2 revolutions, then that would travel at 3.14. So I've got this action. So I'm just going to put another point out here if I made 2 revolutions, which would be actually 4 pi out here. Now, if with this one, when I made 1 revolution, I went 3.14. So if you were to take 1.57 and divide that by 2 pi, what would you get?
1.25.
You'd get the radius. Over here, you'd get a bigger radius of 0.5 meters. So d equals r theta is a linear function, where r is going to represent what?
Radius.
The radius, okay? Or the slope is going to represent the radius. Okay, cool. So, now let's introduce time into this thing. So, as this thing rolls along, let's say we time it. And for the sake of making the math easy, I tell you that it makes 2 revolutions in 1 second. Okay? Just make the math easy, right? So, here's the deal. If I want to make 2 revolutions in 1 second, that means I can write this as nothing but 2 revolutions per second. Now, but I can't deal in revolutions. What can I deal in? Radians. So what am I going to do with those 2 revolutions? I got 2 revolutions. Well, 1 revolution is 2 pi. So I got 4 pi radians per second. Cool with those, okay? Now, here's the next thing. If I take this small wheel here, or this mass, and I roll it across with a smaller radius, and it goes through 2 revolutions per second. And if I take this big wheel here, and I make it roll at 2 revolutions per second, are the linear velocities going to be the same?
No,
Which one's going to be faster?
the wheel,
Why?
because that's a bigger radius.
That's a bigger radius, which means that for every revolution, it's going to travel a
Farther distance.
farther distance. So if you look at V equaling our butt, okay? So let's play this out. So let's say that that's 0.25 meters, all right? And we said that was going to be 4 pi radians per second. Now, this is why this is a dimensionless number, radians are. When you do this, okay, when you do this, and you multiply meters by 4 pi radians, don't write that as like meter radians, okay? It's rare that I say, no, that's why I said this is so unique, because it's a dimensionless number. So when you do this, don't go, oh, meter radians. Is it radians? Yes, but that's why I said it's a dimensionless number. So out of this, you're going to get 3.14 meters per second. Cool. Now, if I did this one, and let's say that has a radius of, I don't know, 5 centimeters. So if I did that and took that 0.05 meters times 4 pi per second, what's going to happen to my linear velocity? It's going to go down dramatically because of the fact that even though it's spinning at the same rate, I'm not going to travel the same linear distance. Got that idea? Cool. Now, believe it or not, every time you guys drive your car, you use this equation. You're going, you've never seen this equation before. Okay, not in terms of your car, sure you have. So, let me give you a quick lesson in auto mechanics. So here's your engine, whatever that may be, and it's going to transfer power out to your differential, and that's going to make the wheels go around. If I could draw a wheel, here we go, back. Okay, so somewhere in here, in this mechanism, there's a sensor that's based upon how fast something is spinning, okay? Depends on how the car is set up. The other thing that happens if you look inside, if you open up your driver's side door, and you should be able to find information about the size of tires that are on your car, okay? It'll say like 30, R35, 15, something like that, okay? You're gonna have different numbers. And that's gonna tell you the size of the tires. So basically, when you look at your speedometer, the engineers have said, okay, V equals R omega. Based upon a certain radius of tire, and this thing, whatever that mechanism is, spinning at a certain rate, that's going to translate into a display for you that says, oh, I'm going 40 miles per hour. Okay? It's a simple equation. It's a linear equation. V equals R omega. Boom. Now, let's say you're going through the rebel phase of your life. Okay? Or the dumb phase, however you want to put it.
Bad and dumb face.
Bad and dumb phase.
Bad and dumb.
Bad and dumb. And you're getting a lot of speeding tickets. Parents are about to kill you, your insurance is about to drop you, bad things are going to happen because you are acting
Bad and dumb.
bad and dumb. So, but you still want to be cool. So what could you do with the size of the tires that where you could still have the appearance of speeding, but you're really not? Would you make the tires bigger, or would you make the tires smaller?
Smaller.
You make the tires smaller. Okay? So imagine that you take off your normal wheels and you put little lawnmower wheels on there. Okay? So you can drive around with your little bad and dumb friends and it's like, look at you, you're going 40, you're breaking the law, you're sticking it to the man. Okay? In reality, you're going 25 miles an hour. Okay? So if you want to have the appearance of speeding without speeding, that's an option. Now, here's another thing that happens, and you don't see this as much, but it's notoriously guys that do this. So guys will do the opposite. They'll buy a truck, and they'll put on oversized tires, okay? I'm going mudding, whatever, Jethro, chill out. So, if you put on bigger tires, and your speedometer says you're going 40, in reality, you're going to be going
60. More than 40.
faster than that. Okay? You might be going 45, 50. So, if this ever happens to you guys, and that happens, and you've changed out the tires, and you go before the judge, and you say, Judge, you know, I was in physics class, we never learned the relationship between radius and angular velocity and linear velocity. Like, I didn't know that would affect that. I will personally go testify against you in court and go, this is a bold-faced lie.
Break this man's knees.
Yes, well, that might be a bit much. So you've been warned, okay? So if you get the urge, like, I want to go buy a truck and put on big monster truck tires, okay? Just realize that's going to impact your speed. Okay, now, speaking of speed. So let's say that I'm going to spin my arm around like this, okay? All right? So here's my arm. Okay, there's my arm. Say it has a radius of 0.50 meters. Okay, boom, there's the radius of my arm. I'm going to spin around like this. So, which point on my arm, close to my shoulder, or my fingertips, and listen to me very carefully, which one of those points, close to my shoulder or my fingertips, has the greatest angular velocity measured in radians per second?
The shoulder.
My shoulder.
Actually, wait, neither.
Why?
They're both traveling the same amount of radius.
Because they're attached to each other.
Yeah.
It's a solid moving object, right?
Yeah.
So if I make one revolution around at that point close to my shoulder, if that makes one revolution, how many radians is that going to move through?
2 pi.
2 pi. Is the tip of my fingers, as I go around, if I make one revolution, is that also going to go through 2 pi radians? Yeah.
Mm-hmm.
Okay? Now, just like, what's the only time you can determine linear velocity and take distance and divide it by time. What's the only time you can do that? You have constant velocity. So the same idea is going to be true of calculating omega. The only time, listen to me, the only time you can take theta and divide it by time to get omega is if it's spinning at a constant rate. If it's speeding up, slowing down, anything like that, you can't do this, okay? It only works if you have a constant angular velocity. So, if you look at this, notice that radius is not part of the story, okay? There's no way to put radius in there. What's the only thing you need to determine omega? Radians and time. That's it. So if my arm was twice as long and I was spinning at the same rate, guess what?
Be the same.
Still be the same. Radius is not a factor. Now, however, which point on my arm has the greatest linear velocity? Now, there's a couple of ways you can view.
Tip of your finger.
Hold on. There's a couple of ways you can view this concept of linear velocity. One is that, imagine that you had like a radar gun, and you're shooting that radar gun at different points of my arm. And the radar gun is going to measure how fast that object is moving in, say, meters per second. Okay? So if that's the case, as this goes around, this would be like 0.1 meter per second. This might be 0.3, this might be 0.5. So if you look at this, because V equals R omega, that V is the linear, sometimes it's called linear velocity, sometimes it's called tangential velocity. Kind of depends upon the problem. But the point being is that radius is a factor in this calculation, but it's not in the omega calculation. Okay? So, here's the other way that you can view this. Imagine that I'm going to move my arm around, and Gapshon is going to try and walk and keep up with this point on my arm. Okay? And Will is going to walk and try and keep up with this point on my arm. Okay? As I go around. So, I got Gapshon close, I got Will out here on the end. Who's going to have to walk faster?
Me.
Will. Why?
It's like running.
Because the radius is bigger.
So what?
Well, radius.
Why do you have to move faster?
Because it increases the speed.
Why?
Because radius is bigger and omega is the same.
Do they both have to travel around the circle in the same amount of time?
Yes.
Mm-hmm.
But he has to travel a greater distance in the same amount of time, so therefore you have to be going faster. Okay? So that's the other way that you can view linear or tangential velocity. Okay? So imagine that you're walking. Okay? Well, where would I have to walk fastest? Closer to the center or further out on the edge? Okay, so stop that for a second. I gotta do the demo and we'll move on.